So in the last couple of sections of the chapter, we're going to look at a couple of different models, but it's important maybe to look at why Lewis model is good and some of the things it can't do. Um, in general, we create models to try to understand the behavior of nature. And we usually try to have the simplest possible model that works to describe all sort of the generally observed features of what we see. Now, Lewis model is actually good at some things. For example, it's pretty good at relative bond strength and bond length. It's good at predicting polarity of molecules. That's based on Vesper theory and Lewis theory both. And then it's good at giving approximations for the bond angles. But here's some things you can't do with Lewis theory. You really can't calculate the actual bond strength or the bond length. So it doesn't really have that kind of predictive power, and it can't be used to get the actual angle. It turns out the angles that were given, right, we sort of hand wave like, oh, for water, the angle is 104.5 degrees, and then we sort of hand wave this because the lone pairs of the electron take up more space. And so, but it can't actually be used to get the actual angle. We just have to measure it and try to understand why the angle is the way it is. And it can't be used to describe resonance really well. And if you remember, resonance gives us multiple structures that describe the structure of a molecule, but Lewis theory doesn't really do a good job of saying what one model looks like. And then the other thing is, it turns out when we talked about paramagnetic and diamagnetic, so when we talked about atoms, right, the atomic orbitals were actually pretty good at predicting whether or not an element would be paramagnetic or diamagnetic, because we could look at the unpaired electrons in a substance and say, oh yeah, it has unpaired electrons, it must be paramagnetic. Or it's all got paired electrons, so it must be diamagnetic. But the problem with Lewis theory is it turns out there are many molecules that are paramagnetic, but in fact, in every Lewis structure you see, except for radicals, right, you always have paired electrons. So even though you have paired electrons in Lewis structures, many of those substances are actually paramagnetic. And so we need something better to understand what are exactly the electrons doing in the structure in order to make it that way. So valence bond theory is the first theory that we'll be looking at. Looks at chemical bonding as an extension of quantum mechanics. And what it does is it takes the orbitals of two atoms and allows them to overlap, and then the overlap is where the electrons will go to form the bond. So these orbital overlaps are between the two atoms. So if we have better overlap, it'll end up being a stronger bond. And if it's a weaker overlap, then we'll find that it's a weaker bond. So when they form the bond, electrons from each atom go into the orbital, the new orbital that's created, or the orbital overlap region, and produce a bonding pair, just like the pair that we would draw in a Lewis structure. And then to account for geometries, because going back to this point, stronger orbital overlap, right, allows for stronger bonds. So one of the things atoms can do to increase the strength of the bond is to do what's called hybridization, or mixing of orbitals, to create new orbital types that have better overlap and better angles so that the groups that are attached to the central atom don't interfere with each other so much. So this is akin to Vesper theory, right? Vesper theory, we say, well, we have these angles. The angles are there so we don't have as much valence shell electron pair repulsion, right? Well, hybridization of the orbitals will help us take that into account. Now, not everything needs to hybridize in order to form a bond. So why don't we take a look at hydrogen, the simplest case. We have two hydrogen atoms with their 1s orbitals here. So at position 1, they're far apart, and you have relatively weak overlap. Remember, orbitals extend out forever. We just think of atoms as being this shape, but the orbitals actually go out quite a ways. But when they're far apart, there's a weak overlap or a weak interaction between orbitals. And so relatively little stabilization for the electrons that are in this orbital. Now, as the orbitals come closer together, what we have is a lowering of the potential energy or of increasing stability. And as the overlap increases even more, this is the most stable point. This is what creates the potential energy well, which is the bond energy. So this right here is my bond energy, and this is my bond length. Okay, so, and again, as we talked about before, as they grow closer together, you can get back to zero potential energy, but because of Coulomb's law, the positive charges of the nucleus and the electron charges begin to repel each other, so they get pushed back and forth. As I mentioned before, in real bonds, this is like an oscillation that takes place back and forth between the two atoms that are bonded. But when we're looking at valence bond theory, what we're thinking about is when the two atoms are at this position here, we think about the electrons being placed in between the two orbitals. So we have a pair of electrons spinning oppositely, because it's still Pauli exclusion principle still applies in this orbital overlap region. So if you've ever seen like a tractor, in the back of a tractor you have a tongue and a slot that it goes in between on a trailer, and there's a pin that you drop in between the two that holds them together. It's like the pin that's holding the two pieces together. So we allow them to overlap, and the electrons fall into this low energy region, creating the stability that we call the bond. So basically, to summarize, what valence bond theory says is bonding takes place between atoms when their atomic or their hybrid orbitals interact, and we call this the overlap region. And to interact, the orbitals are either going to, and this is sort of an extension here, be aligned along the axis between the atoms, or, and we'll show this later, be parallel to each other and perpendicular to the interatomic axis. So I'll be explaining this one later, but you can either have a bond aligned on the axis or off the axis when they're perpendicular.